So it's 5. Okay, so it's recording. So let's start. So what have we done? So we are so we are developing a theory of integration with respect to a measure. So we have a measure space. We start with the measure space. Okay. Then for so we defined for f in some, which we already defined for a positive simple function f equal to summation lambda I 1 ei. We define integral f over x d mu equal to summation lambda I mu of ei. Okay, this we defined for a simple function. So then we also then we verified the following lemma. So then we had the following facts. Every extended real valued positive measurable function can be approximated as increasing limit as fn converges to f with fn in contained in this S plus. So we can approximate it by increasing sequence of simple functions. So then we have defined integral for simple functions. Then we want to define it as the increasing union, and we want to verify that it is well defined. Towards that, we verified the following lemma: if fn increases to f, both fn and f, and this is in S plus, then we know that integral fn, supremum of integral fn equal to integral f. Okay, so this also we proved in the last class. Okay. So now we want to verify that if we define it as the increasing increasing limit of using simple function, then we want that to be well defined. For that, we need the following lemma. So the lemma is, suppose we have two sequences. So suppose we have two sequences of simple functions, S plus, and we have a Gn, which is also contained in S plus, such that they both increase to the same function, such that supremum of n, fn, so x equal to supremum of n, gnx. Okay. So they both increase to the same function, then integral fn supremum over n, okay, d mu over x equal to the same supremum over n x gn d mu. Okay. So if we verify this lemma, then it is clear that we can define the integral of any positive measurable function. This is for a positive measurable function. So positive measurable function is the limit of the limit of the integral of the simple function which converges to that. So it's well defined. That's what this will say. So we have to verify this proof. We have already verified that if simple functions f1 converges to some other simple function f, then the integral also increases there. So we will just use that. So what we do is the following. So we want to consider this supremum of n integral fn x. So we want to show that this is equal to the other integral. So for that, notice that, so did I use this notation? If you have fg, this is just minimum of f and g, okay? This notation. And so you see this f1, if you fix a x, fnx and gnx, they both increase to the same limit. So after some time, if you have any gm omega or something, it will increase to the, that is the following is this, fn omega equal to limit m of fn gm of omega, okay, or I will write it as supremum. Limit is also same as supremum here. This is true because you are taking the minimum, okay. After some time, the gm omega, this is f1, this should be over m. Okay. After some time, this gm, I mean f1 omega and gm omega, they both increase to the same limit. So after some time, gm omega will be greater than f1 omega. So the minimum of f1 and gm is going to be f1 omega after some time. So because of that, the f1 omega, this is same as this. Okay. So you can write this. So because of this, this is equal to supremum of n and m of x over fn gm. Okay. Because because this is a simple function. Okay. This is in S plus. Okay. And this is also in simple function. And the earlier lemma says that if you have simple function with a sequence of simple function which increases to another simple function, then the integral also increases. So because of that, that is true. Okay. Now this is same as, you can supremum, it is just supremum. You can interchange the supremum. If you have doubt about whether you can interchange supremum and all those things, just go through the definition. It is just, you should verify and convince yourself. Okay. Supremum is defined through some epsilon, the definition. You just use the definition, write down, and you will see that it will work. Okay. So this is something you should get convinced. This is same as you can interchange the supremum of n and m. So I have just written the supremum is over n and m. Okay. N cross n or whatever. So this is same as supremum of, so you take the supremum over fn now. So it becomes g. Okay. That's all. So you just, from the earlier lemma, this follows immediately. Okay. So this is clear. The earlier lemma says that if you have a sequence of simple function which converges to another simple function, then the integral increases. So here the simple function, here the fn is a simple function which increases to something. But if you take the minimum with gm, that is a sequence in m, that is a sequence of simple function that will increase us to that. Because of that, this is true. This is by earlier lemma. Okay, this is by earlier lemma. And you can interchange n and m. Again, we are using the same lemma. Same lemma to get this. Okay. So this is just an application of these two things. So this shows that if you have two different sequence of simple function converging to a measurable function, positive measurable function, then the corresponding integral increases to the same limit, same number. The integral is a number, it is the same number. So because of that, we can define the integral for any. So f be a non-negative. So this is lemma is over. Okay. F is some non-negative. This is the difference between teaching in the class and teaching through this. Because when I say something, whether it is clear to everybody or whether everybody is listening, it's not clear to me. In class, when somebody nods their head, then I will know that it's clear. So I will go ahead. So here, even if it is trivial, I may have to say it again and again. Okay. Sometimes it may be very trivial, but I may be explaining it again, or sometimes I may not explain. So if you have any doubt, you have to tell me. Okay. So if we some non-negative measurable function, okay, and fn, we know that fn, we have a sequence simple function such that fn increases to f. Okay, there exists something. Then define integral f d mu over x equal to supremum of n. This is of course numbers, positive numbers. So the supremum certainly exists. It may be infinity. It doesn't matter. So non-negative extended, it can be extended real valued. Okay, it need not be real valued. So, but then that doesn't really matter. It may take value infinity, but when it is something, when the integral is finite, then the set where it takes the value infinity is of measure 0. So you can remove it for all practical purposes. You can remove a set of measure 0 and work with that. So I will make the remark after this. So this is equal to supremum of f1. Okay. So which is well defined. So integral f d mu x is well defined for any positive measurable function, and it is well defined by the earlier lemma, because if you have two different sequences, then the integral is same. Because of that, it is well defined. So then we observe the following, which we call it as remark 1. So if f is some f from x to 0 infinity, some measurable extended real valued function, then if integral f d mu x is less than infinity, okay, then the set x in x such that f of x equal to infinity, mu of this is 0. Okay, if it is not 0, okay, then the integral is infinity. I mean, the integrating over this set, you get infinity, right? Here the value f of x equal to, I mean, you can write. So these things you should verify if you have a. I mean, I have already told you that I mean, the integral is defined like this: integral over any set E f du mu equal to integral of over x f. You just multiply by the indicator function or characteristic function. So this is so this we have defined like this. So if you have a set where where the f takes the value infinity, then the integral over that set itself is infinity. Okay, I mean, if mu of e is positive, if e is something where x in x such that f of x equal to infinity, and mu of e is greater than 0, then the integral over e of f d mu equal to infinity. So the integral will be infinity. So that's why this remark is true. Okay. Hi. Okay. So the second thing is just an observation which we will use in the proof later. So there is this integral f. I mean, I'm assuming it's a positive. It's a positive extended real value function. Integral f mu equal to supremum of all those integral f d mu. Okay, where f is in s plus and f is less than, sorry, this should be g. Okay, so you just take the supremum over all simple function which are, I mean, which are dominated by this f. Okay, this is just clear. I mean, we have already seen the monotone property. For simple functions, we have already verified the monotone property. It just follows because if we have f is, since f is greater than or equal to 0, this implies integral f is also greater than or equal to 0. It's a number which is greater than or equal to 0. So this implies if f is...
That would be integral g d mu.
Integral?
Supremum over integral g d mu.
Correct. Sorry, initially I wrote f, so I wrote the same f here. That is integral g, correct. So if f is less than or equal to g, I mean point-wise it's less than something, then this implies integral f is less than or equal to integral g. So it's so because of this, if f dominates some other function g, then I mean simple function g, this is greater than the supremum. It's greater than all these things, so it's greater than the supremum. On the other hand, this f is defined as the limit of some sequence. Okay, some sequence which converges to this. So I'm not writing this. So on the other hand, f is defined as the sequence, I mean supremum over some sequence, or supremum over subset of something. So this integral will be less than the supremum. Okay, that's because that is how it is defined. Okay, so convince yourself. Okay, so we have the monotone property. Because of monotone property, this monotone, okay, let me write it. This monotone property implies that integral f d mu is greater than or equal to integral g d mu for all g in S plus with g less than or equal to f. Okay. On the other hand, okay, I will write it. On the other hand, integral f equal to supremum of integral fn, okay, where fn is something which is less than this f. So this should be less than that supremum, whatever the supremum we have there. Okay, because it's a supremum over a subset, so it will be less than that. So because of that, this follows. Okay. Okay, so this is clear. So we have a well-defined notion of integration. Okay. Now we want to prove some. What do we want to prove now? So, so we have already proved something called if you have a simple function, sequence of simple function, which converges to another simple function, which increases to another simple function, then we have proved. Yeah. Then we
Uh,
have proved. Yeah. Yes.
like in the last discussion, is f an arbitrary measurable function?
Say it again.
Is f an arbitrary like non-negative measurable function?
Arbitrary non-negative measurable function. Yes. Yeah. It can take. I mean, the integral can take the. I mean, any arbitrary positive measurable function can be integrated. Positive mean it can even take the value infinity. I mean, it's an extended real valued function. Further, we can define the integral. The integral may be infinity. Okay. It's okay. For every function, every positive function can be integrated.
Oh,
Okay. So that's what we have defined. Even if it is extended real valued function, then we have simple function which takes finitely real values. Okay. I mean, our simple function takes the real values. Okay. So we have written this as the limit of real value. So these things can be, I mean, whatever the supremum I have written, the second observation, second remark, here the f is, we assume that they are all real value. They need not take the value infinity. Okay, I mean, they are not extended real value. Okay, so which we will use here. So our next goal is to generalize our earlier lemma, where we proved that if you have simple function fn increases to another simple function f, then the integral increases. So here we want to do the same thing for a general positive real valued function, extended real valued function. So if we have fn, a sequence, or f, all positive, I mean non-negative, we called it non-negative. Non-negative extended real value function. Okay, and fn, I'm not able to write. Fn increases to f, point-wise it increases to f. Okay, they are extended real value measurable. Okay, whenever even if I don't say we are assuming measurable, I mean, we don't consider non-measurable function, so it's all measurable function. Okay, so then integral fn increases to that supremum equal to integral f. Of course, it increases because integral is monotone. Okay. Okay. This is what is called monotone convergence theorem. Okay, or it's called MCT. Okay. Okay. So proof. We will just use our observation. Here we have integral f is the supremum of that, or we can. I mean, we thought that we can do it. So what do we want to do? So first, I mean, as usual, whenever we want equality, we'll prove this is greater than or equal to that. That is greater than or equal to this. So first thing is f is greater than fn for all of that. So this implies integral f is greater than integral fn. Okay, this implies integral f d mu is greater than the supremum. Okay. So we only have to prove the other way. Okay. So we only need to prove the other way. To prove the other way, other inequality, Okay, it is enough to prove. Okay, it's enough to prove. EDB, I always use this notation. Enough to prove for any simple function, or I mean, we have the notation for any s, small s in s plus, okay, integral and with s less than or equal to f, okay, integral s d mu over x is less than or equal to integral this supremum. Okay, it's enough to prove this because f is the supremum of all these values. Okay, you take this s, which is a simple function which is dominated by this f. Okay, then we have noticed that the integral f is nothing but the supremum of all such numbers. Okay, so if we prove that all such numbers is less than some other number, then the supremum is also less than that number. So we are just using that fact. So it's enough to prove for any simple function. It's enough to prove this. Okay. Okay. So to prove this, what we do is the following. So we want to use our earlier lemma, where this monotone convergence theorem MCT is true for simple function. So that's what we will use. So okay. Now notice this is a measurable function. You take the minimum with fn. Okay. But then this fn increases to f. Okay, fn increases to f, and f dominates s. So after some time, this fn, I mean at any point for any x, fn x is going to be greater than this sx. So this is going to converge to s. Okay. Okay. This is clear. We've already used this kind of idea. So this is true. And so because of this, and we know that s is real value. We have assumed, we are not assuming, I mean, even if f is extended real value, yes, we can take the supremum over real valued simple function. Okay. So but it takes only finitely many values, so it's bounded. So since s is bounded, since s, this may not be a simple function because fn's are not simple function. So this will not be a simple function. It's a bounded measurable function. Positive bounded measurable function. So in our lemma, if a function is bounded, then it can be approximated uniformly by simple functions. That's what we have proved. Okay, we can approximate uniformly by that. So can be approximated uniformly by simple functions. Okay. So what does it mean? So this is a function which depends on n. So there exists Sn, a simple function, okay, such that Sn for every point. So when I don't write x, it's true for every point. Sn is less than or equal to less than or equal to there exists what? Wait. Yeah, this is okay. For every n, we can do this. There exists in Sn such that Sn plus 1 by n. This is okay. It's better you mute it and unmute when you want to talk to me. Okay. So we can do this. I mean, this is a measurable function. This is a measurable function. Okay. Can you see the window? Yeah, this is a measurable function. Okay. And it's a bounded measurable function. So you can approximate by a simple function like this. And I mean, you can approximate by a simple function uniformly. Because of that, I'm just writing it like this. But then this Sn may not be increasing. So to make it increasing, we take the following. We define, this is just to for our convenience. Okay, define. Can you just mute your whoever is producing the sound? Can you just mute yourself? And whenever you want to ask question, you can unmute. Okay. So define Tn to be S1. So we want to take maximum here because we want to have an increasing sequence. So S2, S3, up to S7. Okay. I mean, so then it's clearly Tn is increasing. Okay, by definition. I mean, if you take, then you are going to take a maximum with another Sn plus 1. So it's certainly increasing. Tn is increasing. Okay. But then Tn also satisfies this inequality, whatever the inequality we have. Where is it, that inequality? It's here. Maybe we call it star. Okay. Tn also satisfies this inequality. Why does it satisfy? Because if you take any Tnx, this is Tn is a simple T. I mean, if you maximum of simple function is simple function, minimum of simple function is simple function, because our Tn is also a simple function. So Tn is in S plus and satisfy the following. Tnx. So the point is Tnx is going to be xkx for some k between 0 to 1 to n, right? Tn is defined by this maximum. Okay, it's defined like this. So Tn at x is going to be some skx. Okay, so Tnx is going to be skx for some k between n and 1, right? But then this is less than s of fn, fk, right? But then fk is increasing, so that is less than this. Okay, so Tns is less than this. Okay, we have proved this. Tn is less than this. On the other hand, Tn is greater than that, so it's Tn plus 1 by 1 is greater than this. So this is less than. It's Tn is greater than Sn, so Tn plus 1 by n. Okay. So this, it satisfies this, right? Okay. Now this converges to S. Okay. So Tn is increasing. It increases to S, and they are all simple function. Okay, by MCT. We called it as a lemma by MCT for simple function, which we have proved already in the last class. Integral Tn will increase to integral S. On the other hand, integral Tn is less than or equal to integral Fn, because Tn is just the minimum of something. Okay, its integral is less than Fn. Okay, so because of this, it's not writing. Because of this, integral Tn converges to S, integral S d mu is less than or equal to supremum. Integral Fn. Okay. Did I go fast? I thought it's very easy, so I went fast. If we have any problem, doubt, we can discuss now. What we have done is the following. We have proved an MCT for simple function. Okay. So if we have some arbitrary measurable function, increases to arbitrary positive measurable function, increasing to some f, then we took that minimum and we did something, and when we want to prove the other inequality, we took a simple function which is dominated by this f. For that, we proved the inequality, the other way inequality. It's enough to prove that. Okay. So for that, we approximated using some Tn, which is we approximated that simple function, yes, using another sequence of simple function, Tn. Okay. Then that Tn, we had this inequality. Because of that, that will be less than this Fn, and that's why, and that Tn increases to this S. So by the earlier MCT we had for simple function, this is true. Okay. Okay, so I assume that it's easy, which I mean, otherwise also since like it's recorded, you can go through it again, or you can look at the book. It's the same proof. I'm just imitating from. I mean, just I have just taken it from the book. Okay. So what is next? Next one is what is called. It's a proposition, but it's usually called as Fatus lemma. I don't know what is happening. It's not writing. Okay. Is the lemma, Fatus lemma. So the lemma is the following: if Fn are all greater than 0, okay, measurable, extended real valued and all that. I mean, we assume unless we specify it's all extended real valued function, okay, then so what is the idea? Integral over x lim min of Fn d mu is less than, you can take the lim min with an inequality, lim min of integral Fn d. Okay, that's all. Okay. So we want to use the MCT to prove this, the monotone convergence theorem, which we have just proved. We want to use that to prove this. So we are dealing with lim min, and we want to use MCT. That's the only theorem we have. And what does MCT has? If you some functions, some sequence should increase to something, then we will get this. But then lim min is what is lim min? Lim min is limit of an increasing sequence. You take the infimum first, then you take that will be an increasing sequence. So we define Gn or Gm, whatever. Okay, and m is okay. That is equal to infimum. It's lim min, so n greater than m of Fm. Okay, then lim min is this Gm is increasing. This you must be knowing all these things. Gm is increasing and lim min of Fn equal to supremum over m of Gm. Right? It is just the supremum. Okay. So this is a Gm is our increasing sequence, and we want to use our MCT for this Gm. That's what we want to do. Okay. Now Gm increases to lim min. So we have Gm increases to lim min. So by MCT, monotone convergence theorem, we have, what's the time? Okay, we have integral, but I mean Gm increases to lim min, so integral inside lim min for Fn, okay, equal to supremum of over m, whatever, Gm, okay, right? No, yeah, this is over m, right? Yeah, this is okay. Okay. So now we want to prove that this is less than or equal to that. This whatever we have here, this should be less than or equal to that. That's what we want to do. But then that is clear. Gm of x, which is equal to some infimum of Fn x n greater than or equal to n, is of course less than or equal to Fn x for all n greater than or equal to m. Of course, because that is infimum. So this implies integral Gmx is less than or equal to integral, sorry, there is no x here. Integral Fn for all n greater than or equal to m, right? This is true. So this implies this is, I mean, so this is true. So this implies you can take the supremum there, you can take, I mean, then the limit of this is less than or equal to lim min of this, right? This limit may not exist the other way. So limit of this is just the supremum. Supremum of gn over m is less than or equal to lim inf of integral fn. Okay, this we have gone through few times. So this is what we have here. Then this integral supremum gn is that. So this is what we have noticed. Lim inf is inside here. Yeah, lim inf of fn integral is less than or equal to lim inf of integral f. So that's what we have to. So we have proved for Tusslem. Okay. So till now we were dealing with positive measurable function. Now we want to define it for a general measurable function. But then we don't want to. So only problem we have to make sure when we define for a general function is there should not be any problem like infinity minus infinity. For positive function, there is no problem. It will be just positive infinity. Okay, when we define it for a general real valued function, it should not be. So it should not be an extended. So we don't want to deal with extended real valued functions when we deal with which is when we remove the condition, when we relax the condition of positivity, then we don't want to deal with extended real valued function because infinity there may be. Integration is like a summation, so there may be infinity somewhere, minus infinity somewhere. So we don't want to get into that problem. So we want to deal with real valued function, and then in the integral we don't want to deal with something with positive and infinity. So for that, this you might be knowing. This definition, if you have a f is any measurable function, then you can define f plus to be, this is maximum, no? F maximum, the zero. This is O is a zero function, okay? Function 0, taking value 0, okay? Right? And f minus equal to minus of, oh sorry, this is maximum, I'm sorry. Maximum of that, right? Okay, and f minus is minus of f minimum 0, right? If you have minimum of fn 0, will give the either if it is negative, it will give the negative value, and if it is positive, it gives the 0 value. Here, if it is positive, it gives the positive value, whatever that value, and otherwise it takes the 0. Okay, then f equal to f plus minus f minus. Okay, if it's a real valued function, so f is going to take a value which is either positive or negative. If it is positive, then it's going to be this. Here f plus is going to take that value and f minus is 0. If it is negative, f minus is going to take that value, f plus is 0, and because of that, this is true. Okay, I hope so. This is verified, and mod f equal to f plus f minus. So both f plus and f minus are positive number, and f plus f minus are positive functions. Okay, they are both positive function, and we have these things. Okay, these things verify. It's clear. It's direct and it's clear. Okay, verify these things. So now define integral f equal to, now define integrability. We have to define integrability. Define. So this is definition. So okay, maybe definition. F is real valued measurable function, a measurable function. Then f can be complex valued also. Then you have to integrate real part and imaginary part and submit. It's the same thing. There is really integral is supposed to be linear, so you can take the I outside and you can define for complex numbers also, complex valued function also. So then f is said to be integrable then f is if integral mod f is a positive function, is less than infinity. That's all. Okay. So this will imply if mod f is equal to f plus and f minus, they are both positive. Okay, if mod f is integral of mod f is less than infinity, then integral of mod f plus and integral of mod f minus, they are both less than infinity. Okay. So now define integral f d mu equal to integral f plus minus integral f minus. Okay. And I mean, here we have chosen f plus and f minus, but you can, I mean, maybe I will leave it as an exercise. Linear. Okay. Linear means you can take the constant out and you can sum two things. Okay. Okay. So I have 20 minutes more. So I will prove the most important theorem in measure theory, which if you are working anywhere, you will be using again and again in your life. If you are a mathematician, you are going to use it again and again in your life, which is what is called dominated convergence theorem or Lebesgue dominated convergence theorem. Okay, so this is the basic theorem. So we have already seen for two, I mean, we have already seen propositions or theorems dealing with limits and integral. And here the question is, if suppose some fn converges to some f, okay, then does it mean that the integral fn converges to integral f? That is the question. And this answers, this is not true in general. So, I mean, I'll give you a counter example after this. This is true with some condition, some dominated condition. So that is what the statement of the theorem is. So let suppose fn measurable function, I mean real value always, fn f measurable and fn converges to f, okay, pointwise. We have underlying measure space x and all those things, okay, for all x in x, okay, it converges pointwise, okay, and additionally fnx mod fnx is less than or equal to g of x for some measurable g such that g is integrable, okay, then integral fn converges to integral f. Okay. So you should have some function which dominates all this function here, fn. I mean, if it dominates fn, it will dominate the limit also. Okay. So where this function g is supposed to be integrable, okay, if it is integrable, then it is convergence. It converges like this. Okay.
Sir, in the statement of the theorem, you should also mention, I guess, that then f is integrable and this integral converges to this integral.
F is integrable is clear if g is integrable, because f will be less than this. So g is integrable, f is also integrable. That is part of the theorem. You can mention that is part of the statement. I mean, it's contained in the statement. Okay. So I mean, maybe I'll write it here. Okay. Fnx is mod fnx is less than g of x. Okay. I mean, you don't need mod g. G is positive. This is greater than this. This implies f of x is less than or equal to g of x. So this implies integral mod f is less than or equal to integral g. Okay. So which is less than infinity. Okay. So f is also integral. Okay. Now proof of the theorem. So before the proof, counter example. I mean, this is a standard counter example. Later, when you find some other theorem also, we will be using this. I mean, there are only basically there are two examples. One is you will take this integral n infinity, okay, if you want to prove something where something is not true, or we will take this. I mean, you can take that also with 1 by n. I mean, that will not work. So we take counter example. What's happening? Fn equal to n times indicator function 0, 1 by n. Okay. With Lebesgue measure, and mu is Lebesgue measure. Okay. Then what's happening? Then Fn converges to 0. Fnx converges to 0 for all x in x. Right? After some time, this is going to be, I mean, for any x is going to be in some interval. I mean, f is going to be in some, I mean, f is going to be greater than 1 by n. Okay, x is in, for, I mean, yeah. If x is somewhere, I mean, after some time, it will be outside this interval, 0, 1 by n. Okay, for any x, it will be outside this interval after some time, after some n. So indicator function of that point is 0. So because of that, this will converge to 0. Okay. But then this is not a bounded one. This is not dominated by anything. But integral Fn, that is 1. Equal to 1. Of course, n times indicator function. This is 1 by n, which is equal to n times 1 by n equal to 1. Okay. Which does not converge to 0. Okay. Is a standard counter example for this. Okay. You can find other counter example if you wish, but this is a standard counter example. Now the proof, so theorem. So what do we want to? So we have something called Fatou's lemma, and we are just using the Fatou's lemma to prove this. So what does Fatou's lemma says? It says something about lim-inf. You can take the lim-inf by getting an inequality. But Fatou's lemma is for positive function. Did I mention it in the statement? Of course, at the time we had defined only for integral for only for positive function, so I had used it. Okay. So we want to use that. So we want to use it for positive function. That is why we need something dominating that. So we have this function g plus or minus fn. This is positive. Okay. Because fn mod fn is less than or equal to g. So because of that, fn x will be greater. Fn will be greater than g, or it will be. I mean, it will be the minus of that will also be greater than this. So because of that, this is greater than this. Okay. It's okay. Mod of this will be, so because of that, this is greater than or equal to 0. I mean, this is because mod fn is less than or equal to g. So fn is between g, I mean, and minus g. Okay. I mean, it's greater than minus g. Okay. So because of that, this is true. Okay. So I mean, these are all silly things. So you should. Okay. So we have this. Now we know, of course, we know that g plus or minus fn converges to g plus or minus f. That's right. So this implies what? This implies limit. You can take the limit outside. So the limit, I mean, the limit of this is that. So g plus or minus f d mu, which is the limit of this. Okay, and I'm taking the limit outside. That's right. Equal to limit of g plus or minus fn. Okay. Now we can take it, I mean, this is limit, we can take it as lim-inf over n of g plus or minus fn. Okay. By Fatou's lemma. I mean, Fatou's lemma is a real lemma actually. I need not have said this proposition because that will not be mostly used. Okay, this is what is used. I mean, that can also be used because Fatou's lemma is used to prove this, but yeah, that can also be used. When the limit does not exist, you can use that. Okay. Okay. So now what does this say? This says that, of course, integral is linear. So integral g plus or minus integral f is less than or equal to lim inf of integral g plus or minus integral fn. Lim inf. I mean, you can take the lim inf here. But then if you take the positive sign, you can cancel g both sides. That will imply integral f is less than or equal to lim inf of integral fn. On the other hand, lim, what is happening? Suddenly it's not writing. Maybe I have dirtied it. Lim lim inf of minus fn equal to minus of lim sup of fn, right? Because you have maximum, I mean, when you take minus, the infimum, supremum will be interchanged. So this is true, I think. Okay. So because of that, if you have the minus sign, you have the g here. So that will imply that you can take the other way. You can take the minus there. I mean, you will have the minus of supremum. You can take the minus inside, you will have the supremum. I mean, lim sup of that. So that will imply that lim sup of fn is less than or equal to integral fn is less than or equal to integral f, which we have shown that it is less than or equal to lim inf of integral fn. So the limit exists. This implies limit integral fn exists and limit integral fn equal to integral limit fn, which is f. Okay. So we are done. Okay. So maybe I will stop because we have a nice point where we have done this. So I will give. So there is. If you, so I mean, everyone has access to the book by Sundar and Shiva Atreya. There is, so let me look there. So there is, see, when we can take the, when we have a function, so the exercise is the following. So let me just copy it from there. Yeah, so I mean, there is an exercise where you can take the differentiation inside the integral, okay, the partial differentiation. So you are integrating with respect to one variable and you are differentiating with respect to the other variable outside the integral. Okay, I mean, you have a function of two variables and you integrate with respect to one variable, then you can differentiate with respect to the other variable, partially differentiate with respect to the other variable, which is d actually. Actually, it is written though it's not needed. It's a one variable differentiation. So this is what d by dx. So this is over d by dx of integral f of xy. This is y. Of xy dy. You have integrated with respect to y, so it's only one variable. So you can write it like this. So that is equal to integral dou by dou x of f of xy dy. Under some, you can take the differentiation inside under some condition, and that condition is given there. So if dou by dou x of f of xy is less than or equal to h of y for some integral, I mean, this is true for all. Yeah, I mean, this is there are many conditions. So let me not write the whole thing. There are many conditions. So this is just exercise. Two point 2.2.14. Okay, Sundar's book. Okay, so this I give it as an assignment. Next assignment. So I have added this assignment in the Moodle. Those of you who have already submitted something need not submit, but it's up to you. It's better you submit everything in the Moodle by February 5 or something. Okay. I mean, the next class I will finish the Fubini's theorem. So after that, measure theory is over. Okay, we will do a few things and measure theory will be over hopefully by this week or by first class in the next week. So you please submit everything in measure theory, 3 or 4 problems the next week. I will give one more problem next week, and then you submit everything by the end of next Friday. Okay. So yeah.
Sir, won't we be doing the almost everywhere versions of these theorems?
Yes. So there is really nothing new about almost everywhere. You can get convinced about it. So there is something called almost everywhere. So even this Lebesgue dominated convergence theorem is true in almost everywhere. See, the point is this. Fn. So we say some property holds. I don't know, suddenly it's not writing some places. So some property P. This is over. Any property P holds almost everywhere, which you write it like this, AE, if set of all X where P does not hold, okay, mu of this equals 0. Okay. In probability, they usually say almost surely something will happen. I mean, which is actually means surely that will happen. The probability where the set where it does not happen has measured 0, probability 0. It will surely happen. But that's what called as almost surely in probability. That means actually it's surely. That's what it means. So it's almost everywhere means it's except in a place where it is. I mean, this is just a notation. Almost means it's not that it's there is some epsilon where it's close. There's nothing like closeness. It happens. You can just remove that set, which has a measure 0, which is irrelevant for our whatever we do. So.
So this set need not necessarily be measurable, right? I mean, this should be contained in a
it has to be measurable set. It should be measurable, and if it's not measurable, you can't define the measure. So it is measurable, and
so
it.
Like I had seen in some other books that like they just want this thing to be contained in a null set. I mean, that is the definition sometimes. If your space is complete,
that
then
is also you can do, but then that null set is something which has measured 0. No? You can take that set as the. I mean, this is okay. I mean, it's the same thing. What is the difference? You have you have a bigger set which has measure 0, and this is contained in that.
No, but if your measure space is not complete,
Borel.
then like this thing won't be measurable, right? And then you cannot define mu of this.
No, what is the problem? You have a this is may not be measurable, but you have a bigger set which is measurable.
Yes.
Okay? And you can take that set as the definition where this property does not hold. I mean, property may hold.
Does not. Okay, in that sense.
Okay, I don't want to say the property does, where the property holds the complement. Okay, if you want, you use that definition. If you want to be very precise, you let E be the set where the property holds. Okay, E equal to set where the property holds. Okay. Then mu of E complement has measured 0. I mean, this may not be measurable, you are saying, but then you can have a bigger set than E complement where which is measurable. You can remove that set. Outside, see, the point is outside a set of measure 0, the property holds. That's what it means. Okay. That's what it means by it's true. Something is true almost everywhere means it is true outside a set of measure 0. Okay. You don't need to worry about these measurability problems here. Okay. Because you always have a bigger set where it is measurable. Okay. So the point is, if you have some limit exists almost everywhere, suppose F1 converges to F, okay, almost everywhere. That means the set where this happens, where this convergence happens, has, I mean, where this does not happen, is at most a measure set of measure 0, okay. Then this set, this corresponding, say to start with, this is the point. The set where limit Fn exists. But of course, Fn is measurable, F is measurable. Then the limit exists is a measurable set. Okay. All those X such, I mean, this all those X such that limit Fnx exists is a measurable set. We have already seen. We have already seen the following when we discuss measurable function. If F is measurable, G is measurable, then the set F equal to G, where the points where F and G are equal is measurable, is a measurable set. Okay. Then if we have any measurable, a sequence of measurable function, lim_inf is measurable, lim_sup is measurable. Limit exists means lim_inf is equal to lim_sup. So the set of points where the limit exists is a measurable set. Okay. So these things make sense. Okay. So you can remove a set, you have a set of measure 0, then you can integrate it. So if you have an integral over x, you can integrate it over e, and you can integrate over e complement. So this will have measure 0, then you can work with this, and you can even remove this set. You don't have to worry. So verify, convince yourself what's happening here. Okay, convince yourself or verify. Okay, anyway, it's going to end, so I don't need not worry about this. Verify LDCT, the Lamech dominated convergence theorem, for almost everywhere convergence. Okay, it's the same thing. Okay, there is no difference. If it converges almost everywhere, that is enough. Okay, so that's the point. Okay, so it's 6 o'clock. I will stop and we'll meet.
Sir, so for the in the statement of LDCT, like where you need Fn converges to F pointwise almost everywhere, and you also need to mention that F is measurable, right? Because if a measure space is not complete, then like that thing. So either like you have to take the space to be complete or the F to be measurable.
What is the problem? The limit of measurable function is measurable. What is the problem?
No, but you are taking almost everywhere, right? Now
Almost everywhere means outside of measurable set, this is happening. And the limit where it exists is always measurable.
And video.
No, what I am saying is that the pointwise limit, that thing need not. That I mean the pointwise limit, and then you are taking the almost everywhere thing. So unless your space is complete, as it is a complete measure space, then this thing need not necessarily be measurable. So
when we say almost everywhere, outside a set of measure 0, a measurable set, f and the conversion happen, and there it is measurable. I don't see how will there be a problem. See, whenever we say almost everywhere, it happens outside a set of measure 0, and that set is a measurable set. Okay. So
So what I'm saying is that this is definitely false, right? That the pointwise limit of so if f is almost everywhere the pointwise limit of a sequence of measurable functions, then that is not.
F is a pointwise limit of measurable function. Okay.
No, f is not the pointwise limit. F is almost everywhere the pointwise limit of measurable functions.
Almost everywhere pointwise limit. No, what do you mean by almost everywhere pointwise limit? It just converges almost everywhere. Okay. So it happens outside a set of measure 0. Okay. So if you restrict that function to that space, it is measurable. And here you have a function, you can have some measure. I mean, in the set of measure 0, you can define it to be 0. I mean, the point is, when you talk about almost everywhere, you don't, I mean, on the set of measure 0, the point is, I mean, what is your point is, on the set of measure 0, you can have the function to be some non-measurable function. I mean, you can replace it by a different function, which is not measurable. Okay, your point is you can replace it by a different function, and that will also, yeah, you are right actually.
Yeah.
By a different function, then the almost everywhere convergence will also follow. But by definition, we are assuming, okay, yeah, that is right. So you need F to be measurable. Yeah, you have to say that F is measurable, or you can always replace it by a measurable function. Okay.
Or
maybe like we can just restrict to complete measure spaces, then these issues won't arise.
No, usually we will work with Borel measurable function, Borel sigma algebra. So
okay.
It will not be complete. So we will always assume these things. Okay, F is measurable and all that. Or we can always replace it with a measurable function. Okay. When we see the point, I mean, it is just for practical purposes. See, you want to be precise and you are saying this, but the point is we are having the set where it does not, this thing does not happen. That is a measurable set. You can replace it by a constant, some function, constant function or something. You can replace it by a measurable function, then this will be true. Okay.
Yeah.
Okay, so this is okay. Okay. So,
Sir, just a second. So, like the other assignment, right? Should we separate? There was a question given now. So, should we submit it together, or is it okay if we submit?
whichever you can submit it together. I mean, it's just electronic, no? So you
Okay,
can
fine.
see a copy. So you can just, I mean, you can submit it in the Moodle, or if you have already submitted, you need not submit. It's better you submit it again in the Moodle. Okay.
Oh, okay.
Okay, all of you submit in the Moodle again. Everything, whatever you have, it's just same file. Okay. Okay. So I'm not seeing anything here. Okay. See anything else?
No.
Okay. If nothing,
Sir, can I give a presentation next week on Petusch measurability theorem?
what is it? Let me look at it. So you, what measurability theorem?
Petusch measurability theorem.
Okay, but see, we want to do something which is consistent with what we do here. So let us see. I mean, this week he will do Lebesgue integration, Riemann integration. If you want to do something else, you can do it. Let me think about it and tell you. Okay. Hmm?
Okay, sir.
Okay.
Okay, sir.